Hi, everybody. This is going to be chapter number 7. We're going to get into a couple of different things. We talked about a little bit in our last class. We talked about atomic structure, what an atom consists of, not only what it consists of, but where they're found. We also talked about ionization energy, electron affinity, and everything like that. And we talked about periodic trends. Now what we're going to get into is transitioning a little bit away from single atoms and ions, but instead we're going to begin talking a little bit more intensively about structures of molecules. So in just one, so this is one of the things that we discussed on Wednesday, the different types of bonds and the corresponding different types of molecules. But what I'd like to move to now is a discussion of valence electrons. If you remember, whenever we talked about the structure of an atom, we talked about valence electrons. Those valence electrons are the electrons that are farthest out in a given molecule or in a given atom. And one of the things that I'd like you to really kind of focus in on for this module and for this group of material is we're going to be largely focusing on the things on the far left-hand side and the far right-hand side of the periodic table. And the reason for that is they have a little bit better trends that you can follow. But that's also because this block in the middle, those are your transition metals, and these can do a number of different things. But if you remember, whenever we were talking about electron configuration, that's where we talked about our so-called S, P, D, and F orbitals, and placing electrons in there. If you remember your S orbital, we had 2 electrons that we could put in there. Our P orbital, we could put a total of 6 electrons in there because there are 3 different positions. The D orbitals, we could put 10 electrons. And then the F orbitals, we could put 14 electrons in there because there are 7 different positions. Now, this figure at the bottom is really kind of an extension of this or it's zooming in on the periodic table, and it's showing us basically the number of valence electrons in these different atoms based on where they are in the periodic table. For instance, if we look at something like beryllium in group 2, it has 2 valence electrons. That means that, or in particular, it's got 2 electrons in its 2s orbital, the outermost orbital. If we look down at barium, also in group number 2, it also has 2 electrons in its outermost orbital. If we look at group 3, which is right here, we've got boron, aluminum, gallium, indium, and tellurium. I believe that's tellurium. They all have a total of 3 valence electrons. And then if we go all the way over to our noble gases in row 8 or in group 8 of the periodic table, all of those except for helium have a total of 8 valence electrons. Helium has 2 valence electrons, but its largest orbital is that 2s orbital, and that orbital is filled. Okay, so this is a nice model for, and this is an important model to look at how many valence electrons does a given element have, and how do you draw that atom, or how do you draw what's called a Lewis dot structure for these different elements. The way that you do it is depicted, and I think you probably picked up on this from the models that are provided. If we take something that has 4 valence electrons, like carbon, what we're going to do is write the symbol and then start in kind of a clockwise fashion and add however many electrons it has, or however many valence electrons it has, outermost electrons, in one of 4 positions around that symbol. If you take something like oxygen, well, oxygen, I'm sorry, not a clockwise fashion, in a counterclockwise fashion. Oxygen, we're going to do 1, 2, 3, 4, 5, 6 valence electrons. So what that means is it has 6 electrons. If it were to add 2 more electrons, which oxygen has a tendency to do, then it would get to the noble gas electron configuration, or the same electron configuration for something like neon. Now let me clear all that writing, clear all drawings. Now, the octet rule is the rule that we follow. atoms will share or transfer electrons to achieve 8 valence electrons. An octet, 8 valence electrons, 8 octo, octagon, octopus, octagonal. That's kind of octagon, but nevertheless. In ionic bonding, in the case of an ionic compound, what we're doing is we are transferring electrons completely from one element to another, and the other element is accepting it. And so we draw something like sodium chloride in this way right here, where we're going to show Na has lost an electron. And then Cl has accepted that. If you look at chlorine, which is in group 7 of the periodic table, it has 7 valence electrons. But in this model that we've got right here, we've got 2, 4, 6, 8 electrons. That is one more than it generally has, which is why it gets that negative charge there. Now that's an ionic bond, so that's a total transfer of electrons. Meanwhile, if we look at covalent bonding, when it comes to covalent bonding, what we have is sharing of electrons. I depicted this in class the other day by drawing something that was a little bit, there we go, something, or another way that you can model HBr would look like this, HBr. And this single line right there represents a sharing of 2 electrons. Something like H2S would look like this right here, where S rolls in with a total of 6 valence electrons. Each hydrogen rolls in with 1 valence electron. And another way to depict H2S would look like this. H, boom, 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 boom. H2S. The last molecule down here, well, that's nitrogen, which is sharing a total of 6 electrons. So what that looks like is this. 1, 2, 3. So that's 3 bonds. So that's 6 electrons. 1, 2, 1, 2. And now I talked about how this nitrogen has 8 electrons around it. And then this nitrogen also has 8 electrons around it. So that's kind of the important parts about the octet rule and the differences between covalent and ionic bonding. Ionic bonding, one atom or one element has lost an electron or electrons, and the other has accepted it or accepted them. And it ends up with an overall negative charge. So the Lewis structure, as is depicted here, we have that sharing of electrons. Sharing of electrons to make covalent bonds can be demonstrated using Lewis structures. We start by trying to give each atom a filled outer energy level, or its octet, by sharing electrons. The simplest examples are H2 and Cl2. Those are both diatomic elements. Now, when we look at, say, hydrogen down here, hydrogen down here, H2. Each one of those hydrogens brought 1 valence electron. It's 1s electron. It has only 1 electron in that s orbital. So each hydrogen has an electron configuration of 1s1. Whenever they share, when each hydrogen contributes its electron to that overall molecule, each one of them has a full octet. Even though they don't have 8 electrons, they each have a full outer shell, which is that s orbital. They both have the electron configuration of something like helium. Now, when we talk about Cl, Cl has a total of 7 valence electrons. And here what we see is Cl2. Each one of these molecules, each one of these atoms has 7 valence electrons, but they're sharing one of their valence electrons, which gets each of them to a complete octet. So we can have either a covalent bond where electrons are being shared, or we depict an ionic bond where electrons are lost by one species altogether. Now, in our previous slides, we looked at chlorine. We also, in a much earlier slide, we looked at, N2 or nitrogen. And there's actually what's known as a triple bond between those two atoms. So some atoms share only one pair of electrons. These are called single bonds. They're reflected by a single line. Sometimes two pairs need to be shared. These are called double bonds. And sometimes, as is the case with nitrogen, N2, there's what's known as a triple bond, where there are a total of 6 electrons ultimately being shared between those two atoms. Oh. Now, in order to write a Lewis structure for a molecule, what you need to do is you need to account for the number of valence electrons that any and all of the atoms have. So you need to first sum the valence electrons for all atoms, taking into account the overall charge. So if it's an anion, add 1 electron for each negative charge. If it's a cation, subtract 1 electron for each positive charge. In this case, we've got PCl3. When we look at the periodic table, what you'll notice about phosphorus is that it is in group 5 of the periodic table. So you might see that depicted as row, I guess that would be 5A. So P right there has a grand total of 5 valence electrons. So that means it's got 2, and I like to do this just kind of like keep my mind fresh on the material and the idea. We've got 2 electrons in the s orbital, and then 3 electrons in that p orbital. And since phosphorus is in the third group or third row of the periodic table, that means it's got 2 electrons in the 3s orbital, 3 electrons in the 3p orbital. After we've got the number of electrons that phosphorus brings to the table, then we got to look at the number of electrons that chlorine brings to the table. And we have to take into consideration the number of chlorines. We have a total of 3 chlorines. Each chlorine brings in a total of 7 electrons. So 7 times 3 is 21. So the total number of electrons that we have with something like PCl3 is 26. Now, if we wanted to draw that molecule, that convert from this structural or this molecular formula to the structural formula, what we've got to do is figure out which symbol is attached, or which element is attached to which element. Now, the least electronegative element, which we haven't talked about electronegativity quite yet, but the one that is farthest to the left on the periodic table is generally going to be the one that's in the center. Now, there are some exceptions to that rule, but as is life, learn and follow the rules, and then as time goes on, adapt and figure out the exceptions. So phosphorus being written farthest to the left, that's going to be in the center. And what we're going to do from that is we're going to draw single lines to each of our chlorines. Now, what's worth thinking about right here and right now is if we've got PCl3 and we've got a single bond going to each one of the chlorines, how many electrons is that? Well, right now, we've drawn a total of 6 electrons. Each one of those single lines equates to 2 electrons. So one of the things that I always like to think about and ask is, how many electrons does phosphorus see? Well, phosphorus sees a total of 6 electrons, because each one of these lines is 2 electrons. So phosphorus has 6 electrons around it. So does phosphorus have a complete octet? It does not. It has 6 electrons. It needs 8. We're going to get there, but we're going to get there. Okay, so now we have 20 electrons left to draw. Nope. And we need to complete an octet for each one of our chlorines and our phosphorus. Well, to draw the complete octet for chlorine, you just put electrons, 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 boom, 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 boom. So each one of our chlorines has 8 electrons around it. That's 3 species where we drew 6 additional electrons. That gets us to 18 electrons, so we can subtract 18 from our total of 20 electrons that we had left. So now we're left with only 2 electrons. We're left with 2 electrons. Chlorine has a complete octet. Other chlorine, or all 3 of our chlorines, have complete octets. The only thing that does not have a complete octet is phosphorus. So now what we're going to do is use those last 2 electrons, put those on phosphorus. Phosphorus has a complete octet. Each one of the atoms in this molecule has a complete octet because we followed this last rule, which was any excess electrons go onto the central atom. So what we're going to do is we're going to put any electrons that we need on our central atom. Any of those that we have not already drawn, that's what we're going to do. Now, in some instances, if there are not enough electrons to give a central atom an octet, well, then what we're going to do is we're going to introduce double bonds and triple bonds, multiple bonds here. So HCN, the way we've drawn it here on the left-hand side, has hydrogen with a full valence shell. It has 2 electrons. It's sharing 1 with carbon, and carbon is sharing 1 with it. Now, on the left-hand side again, where we've got carbon. Well, carbon only sees 4 electrons, and carbon needs to see 8 electrons. We've got nitrogen seeing 8 electrons, which is what it needs to do, but we can also redraw this by taking the electrons here and here that are indicated by this red line, and instead making those 2 electrons this and this respectively. So we go from a single bond to a triple bond. Okay. So there are some, like every element is supposed to have 8 electrons around it, but there are some exceptions. Hydrogen is one exception. It only needs 2 electrons. Be, also known as beryllium, only needs 4 electrons. Boron, B, needs 6 electrons. So there are these 3, hydrogen, beryllium, boron, as elements that can go under 8 electrons around them, and they are happy as a clam. Then there are exceptions that we will see that exceed 8 electrons. Phosphorus, for instance, can have a total of 10 electrons around it. Sulfur can have 8, 10, or even 12 electrons around it. We'll see these with some more complicated or some more complex models in just a little bit. Now, it's pretty common that carbon's going to have a total of 4 bonds coming off of it. And what that means is it's not going to have a lone pair of electrons, which an example of a lone pair of electrons would be this right here is a lone pair of electrons. They are not being shared with anything. Those 2 electrons are by themselves on that nitrogen. So carbon generally is going to have 4 bonds off of it. It's going to either have 4 single bonds, 1 double and 2 singles, or 1 triple and 1 single. We see that with HCN. Carbon here has 4 bonds coming off of it in the form of 1 single bond and 1 single bond and 1 triple bond, accounting for or amounting to a total of 4 bonds. Now, nitrogen generally is going to have 3 bonds and 1 lone pair of electrons. Oxygen is generally going to have 2 bonds and 2 lone pairs of electrons. Know these common bonding patterns, and it's going to help you out tremendously when you're drawing molecules. Your halogens generally have 1 bond and 3 lone pairs of electrons, and carbon bonds to carbon first. Whenever you see a molecule that's like C2H4 or something like that, draw that carbon to carbon bond first and then fill everything else in. Now, like I said, there are some atoms that can have more than 8 electrons. And the way that they do that is by taking the places that they have their valence electrons. If we take phosphorus, for instance, phosphorus will have a total of 5 valence electrons. It's going to have an electron configuration with 2 electrons in the 3s orbital and 3 electrons in the 3p orbital, which is depicted at the top of the screen here, right here. Now, what phosphorus is capable of doing is it's able to do what's called hybridizing orbitals. So it can take these orbitals right here, this S, this 3s, these 3p's, and this 1d orbital, and make an orbital that is partially s, or it's 1 part s, 3 parts p, 1 part d. So that's where this terminology sp3d comes from. It's 1 part s, it's an orbital that is 1 part s, 3 parts p, 1 part d. There are some elements that they can take orbitals and say, I'm going to make an orbital that can be 1 part s, 3 parts p, 2 parts d, and that would be sp3d2 hybridized. So basically what this does, if we go back to the example of our sp3d hybrid orbital, this right here, those are all unshared electrons. So what this allows is something like something like fluorine to come in and say, hey, I have a single valence electron, and that fluorine can then pair up one of its electrons with an electron here, and here, and here, and here, and here. So this is a very important point. A hybrid orbital enables expanding or exceeding the octet rule. So hybrid or orbital hybridization allows for exceeding the octet. As we see here, like I said, an sp3d2 orbital. Sulfur has taken an s orbital, 3p orbitals, and 2d orbitals to make an sp3d2 hybrid orbital, allowing for sulfur to basically have a larger number of shared electrons. So by hybridizing orbitals, by making an orbital, a place where an electron is, making it look like multiple different places, these certain elements can exceed the octet. Now, with that in mind, when different atoms share electrons, those electrons are not shared evenly. So if we look at, and there's a phenomenon known as electronegativity. Electronegativity is basically a measure of kind of how badly or how much does one atom want the shared electrons. So there's a trend on the periodic table about electronegativity. And the most electronegative element, most E negative, is fluorine. So anything between any element sharing electrons with fluorine, fluorine wants those electrons more than that other element. If it's carbon and fluorine, fluorine wants the shared electrons more. If it's nitrogen and fluorine, fluorine wants the electrons more. Fluorine always wants those electrons more. Now, with that in mind, when we have a bond where electrons are not shared evenly, this is known as bond polarity. So bond polarity is where one atom wants electrons within a bond more than the other. There are bonds that are considered to be non-polar covalent bonds. So non-polar, there's no pull, there's no strong pull, because each atom in that bond wants those electrons equally. So they basically cancel one another out. There are covalent bonds where electrons are being shared, but one of those elements wants those electrons more. And then there's an an ionic bond where one species, one element, one atom wants those electrons so much more than the other that the other just says, fine, you can have them. At the bottom of this slide, we have chlorine gas, or Cl2. Cl and Cl. Both of those things are going to be pulling those electrons equally. It's a game of tug of war that there's no movement. That is an example of a polar or a non-polar covalent bond. There is equal and opposite forces. A polar covalent bond is where one element, chlorine and H over here, chlorine's pulling as much as it can, and hydrogen's basically saying, like, you're pulling stronger than me, so but we're, I'm putting an effort in. I haven't given up in this game of tug of war, but you're winning. An ionic bond is where a Jeep matches up against a fence post. That Jeep, and I'm talking about a fence post that's like just sitting on top of the ground, basically. The Jeep pulls and it takes the electron. It wins that game of tug of war infinitely. So that is an ionic bond. So we have a spectrum here. We have a range, a non-polar covalent bond where the electronegativities cancel out. A polar covalent bond where one atom has a greater electronegativity than the other. And then an ionic bond where one atom has such a greater electronegativity than the other that there's really no competition. So fluorine is your most electronegative element. And the trend is things in the upper right-hand corner of the periodic table, which I'm going to put a little stamp by. I'll put a little arrow here. Things in the upper right-hand corner of the periodic table, as I've shown right there, those are the most electronegative, with fluorine being the most electronegative element. Now, this is basically that same trend that I just described on the periodic table. And then this bond polarity ranges from a purely nonpolar bond to a polar covalent bond to an ionic bond. How the magnitude of these differences. Now, this is the sort of question that I will ask of you. So a polar bond, or bond polarity, is determined from the difference in electronegativities of two elements that are involved in a polar covalent bond. What we do is we look at the difference between those electronegativities. And this scale at the bottom gives you the range. So a bond is considered to be nonpolar, it's a nonpolar covalent bond, if the electronegativity difference is no greater than 0.4. So if the electronegativity difference is 0.1, 0.2, 0.3, 0.4, it is considered to be a covalent bond. Those electrons are being shared very evenly amongst one another. A polar covalent bond is when the electronegativity difference between our two atoms is greater than 0.4, but no greater than 0.2. So if we look at carbon and oxygen, carbon has an electronegativity of 2.5, oxygen has an electronegativity of 3.5. If we take the absolute value of 2.5 minus 3.5, our electronegativity difference is 1.0. That is between 0.4 and 2.0. That means that this is a polar bond. If we look at magnesium oxide, or MgO, what's our electronegativity difference there? And actually, before you even get into that, magnesium is a metal, oxygen is a nonmetal. Magnesium's electronegativity is 1.2, oxygen's is 3.5. Our difference there is 2.3. That bond is so polar that it's considered an ionic bond. So think of this as a continuum or a spectrum. A bond is so polar that it's gone beyond polar and it is considered ionic. Then, and so I will give you this information, these electronegativities, and ask about bonds. I'll say, here's electronegativities, classify this bond as polar, nonpolar, ionic. These ranges, 0.0 to 0.4 to 0.2 to 3.3, that's your difference, or that's your differences for classifying different bonds. All right,